It's about 25 degrees outside, so I thought it'd be a great time to come in and get under some studio lights and warm up a little bit. So what is a frequency? Right now you may be thinking, oh, it's waves and it's channels and all of this. But I want you to think, what is frequency? Just very simple. Without being technical, think about what is frequency. Pause the video if you have to, but take a moment to think about it. Frequency is how often something happens over a period of time. Your heart rate may be 60 beats per minute. That is a frequency. If you're traveling down the road at 60 miles per hour, that is a frequency. So in Wi-Fi and radio frequency, what are we talking about? We're really referring to this, the magical wave, this thing that we see in pictures and on these fancy machines. But what is this wave? Now, this wave can come in many shapes and sizes. That doesn't really matter right now. We're just kind of looking at this wave very simply. So a wave is a 360-degree movement of a signal, of energy. Radio waves are actually, they're invisible, of course. You can't see them. But they are in the electromagnetic spectrum, just like light, visible light and X-rays and all this. All frequency is just some different frequency, whether we can see it or we can't, or something like radio, which we use for communication. Now, this in particular, we can look at this as a circle. 0, 90, 180, 270, and 360 degrees, which, as in a circle, we're really back to 0. So this frequency is pretty important. It's something, radio frequency. Where did the frequency come from? Well, the frequency came from a guy named Heinrich Hertz. You've probably recognized the name Hertz. In fact, we're going to talk about it right now. This gentleman, Mr. Hertz, actually discovered the existence of electromagnetic waves. It's pretty interesting to read about it because when he discovered it, hey, it's a pretty cool discovery. Too bad nothing will ever come of it. If he could only see us now. It's a pretty big discovery. So Hertz is abbreviated Hz. That's why every time you see megahertz or gigahertz, the H is always uppercase. So a hertz, 1 hertz, is 1 cycle per second. All that means is the wave makes some motion, which can be any shape. As long as it starts at 0 and ends back at 0, 360-degree movement of a wave is 1 cycle. Now, if we were to look at this, if this is 1 second in time, here to here, that would be 1 hertz. In the world of everything, that's a really low frequency. 1 hertz is basically, we don't even talk about something that low. A 1 hertz sound wave would vibrate you crazy. Like a low bass, like if you hear like the coolest bass you've ever heard, it may be like 17 hertz. It's really, really low and deep. In the world of RF, this basically would barely even exist. So with frequency comes a few other things, a few other terms that we should probably learn. The first is amplitude. Amplitude is the height of the wave. The height. This wave has a higher amplitude than this wave. What does amplitude mean? Think of amplifier. What does an amplifier do? It increases, we usually think of that in maybe our stereo system, it increases the volume, the amount of energy. The same thing happens in an RF wave. The more energy, the more signal strength, that higher the amplitude, the higher that wave is. So frequency is just how often this happens. The height, the amplitude, is how strong it is. It doesn't change the frequency, it does change the height, which is amplitude. The other is phase. So phase must be relational. If I just draw this and ask you what phase it is, your answer is, I don't know. There's nothing to compare it to. If I do this and say, all right, what phase relationship do these have of each other? Well, they are exactly opposite. In the world of RF, we call this 180 degrees out of phase. Why would we call it 180 degrees out of phase? Let's do some erasing here. and Cy. So if we look at just a continuous wave, and we draw the same thing here, okay? Again, if I'm a perfect artist, you'll see that these match up perfectly. These are in phase. They are exactly the same. If you draw the 0, the 90, the 180, etc., sorry, the 180, the 270, etc., and these will match perfectly with what we have down here. What I drew here was an out-of-phase signal. Now, this is where things get a bit complicated, at least complicated sounding. How would this bottom one, we'll call this 2 versus 1, how would number 2 become 180 degrees out of phase? The shape of the wave doesn't change. What changes is time. What if all of a sudden this second one was delayed a little bit? So we'll call this one 2b. We're going to say the time has changed. And now, what if we start here? Okay, so the wave is the exact same shape, but the time was delayed just a little bit. We delayed the time slightly to now we are exactly opposite, which is 180 degrees out of phase. So phase is the relationship between two signals. What does this matter right now? Not a whole lot. It's really important as we move on to advanced topics, transmit beamforming, multiple input, multiple output, spatial multiplexing. All of this becomes very relevant. But for this lesson right now, just understand that phase is the relationship between two signals. And in this case, we have two that are in phase and two that are 180 degree out of phase. And these can be any number. You could have 90, 180, 270, any number in between could be representative of the phase. So let's go back to frequency. One of the more important topics we have here today. Do my best to get most of this off right now. Okay. So let's go back to this. So back to the frequency. First, let's look at some different frequencies. We know that it's how often something happens. What would that look like? Let's look at a highway for an instant. So let's say you're looking at the highway closest to your house. You decide to get up one morning and do something kind of crazy. You're up at 5 a.m. and you are going to you're actually going to count the cars. You're actually going to see what the frequency is. Now we're going to say the speed of all the cars is 70 miles per hour. If you live elsewhere in the United States, I agree we should be on the metric system, but it's what we have. 70 miles per hour, it's a constant speed. These are representative of cars. 70 miles an hour, you count 20 cars per minute. We have established a frequency. 20 cars per minute is a frequency. At 9 a.m., you count 100 cars per minute. Now, the speed hasn't changed. Everybody's going the same speed, although in real life they would slow down because of traffic. But we're saying this is a constant. So what happens when you add more cars? The distance between the cars gets closer. This is called wavelength. Wavelength and frequency are they're mirrored together. In RF, the radio waves travel at about the speed of light, 300 million meters per second. It's pretty fast. So we use that calculation to determine this. So in frequency, a higher frequency may look like this, where a lower frequency may look like that. Obviously, a higher frequency is more frequent. It's happening more often. This is a higher frequency. There's more cars going on per minute in this case. There's more cars traveling. The cars get closer together. In RF, since the speed of light is a constant, the higher the frequency, the closer the waves get together. Now, when you measure these waves, which can actually be done with a little bit of math, that is called wavelength. And wavelength is actually truly measured in centimeters and meters. It's measured in length. In fact, if you know someone that's an amateur radio operator, ham radio operator, they actually will talk in wavelength, not frequency. They may say, hey, Joe, what are you doing? I'm on the 2-meter band. When they say the 2-meter band, they're actually meaning their wavelength is 2 meters long. In Wi-Fi, there are different frequencies. So let's explore a few frequencies. You may be familiar with something like this, 94.1 megahertz. That means, this is a local radio station here to me, that radio station means its frequency does one cycle 94.1 million times per second. It does a full 360-degree movement 94.1 million times per second. That's a lot. That's a pretty high frequency. In Wi-Fi, we have higher frequencies yet, 2.4 gigahertz. That means the cycle is 2.4 billion times per second. Now we're getting up there. Another Wi-Fi frequency is 5 gigahertz. There's actually other frequencies that will maybe eventually used and could be used today, but they're less common. These two are current Wi-Fi frequencies that are used. Now, what's the difference in frequency? What does it matter what frequency we're on? Have you ever been at a stoplight? You're in town, you stop at a stoplight, and you hear someone else's stereo. What do you hear? The bass, right? Boom, boom. You're hearing the bass of the car. It's because the guy can't afford tweeters? Probably not. The reason is low frequencies travel farther. Low frequencies in radio can be received at greater distances. The farther away you want to transmit a signal, lower frequencies enable you to do that. If you think of radio versus Wi-Fi, or your TV versus Wi-Fi, AM radio versus FM. AM goes much farther. It's lower frequencies. So lower frequencies can be received farther. So is there a downside? Why don't we just use really low frequencies? The upside of high frequencies is something called bandwidth. Bandwidth is something we will discuss in more detail, but the simple fact is bandwidth is like highway lanes. The wider your highway, the more traffic can move down it. Bandwidth is the amount of frequency you're given. Imagine 1-lane road is one frequency. We could call that one channel. Or you could have a 100-lane road, that's 100 channels. Which would you rather have for moving traffic? Give me the bigger one. Low frequencies have less bandwidth. They can't move as much data. So there's this balancing act. And oddly enough, these frequencies right here are actually really good for Wi-Fi. They can transmit a fair amount of traffic today, over a gigabit with today's technology. And the range is somewhat acceptable. Ideally, the range is huge and the speed is huge. You don't get that. With the way Wi-Fi, or the way basically digital communication works, you can't have both. The higher the frequency, the more speed you get. So we've explored amplitude, the height of the wave, phase, the relationship between two or more signals, wavelength and frequency, which are basically proportional to each other. The higher the frequency, the smaller the wavelength. In Wi-Fi, in 2.4 gigahertz, this is about a 12.5 centimeter wavelength, so you could actually measure that. And this is a lot easier to remember. It's at 5 gigahertz is about 5 centimeters. How does this impact us? When we get to the antenna section, you're going to say, aha, now I know why antennas are a specific size. Now I know why cellular is a certain size and my TV antenna is a certain size. It's all back to here. So hopefully this gives you a good idea, a good solid start in frequency, amplitude, phase, and wavelength. Let's keep moving on.